Okay, so today we're going to talk about balanced trees. So balanced trees, if you remember from last week, right, we were talking about trees. So this is like a natural extension of trees. You have, well, balanced trees, which are just trees that are balanced. And okay, so don't worry about that slide, not relevant for us. But yeah, we're going to be talking about project one a little bit, and quiz question and trees. So for the Giddy Reveal project, which is our project, right, we have, you're going to be doing insertion, remove, search, and traversals for the AVL tree, I believe. And yeah, for insertion, you'll need to implement rotations to fix imbalances after insertion. So yeah, but hopefully, yeah, if you've already looked at the project, that's good. And then also for this, yeah, like this project is on AVL trees, which we're going to talk about today. So hopefully after today, you'll have a better idea of what they're all about. So yeah, for the project, you mean designing interface, modules, functions, parsing input, and building a main. And okay, that's just kind of an overview of the project. And for grading, okay, yeah. Okay, wait, oopsies. Okay, so enough about that. So let's talk about balance trees. So hopefully, yeah, I mean, the project, like if you have questions about it, of course, you can like message me or something on Slack or email. But the general idea of the project is you're building an AVL tree. So hopefully if you understand what's going on today, you'll understand the project really well. So why balance trees? Okay, well, let's talk first about what you have with unbalanced trees or just regular binary search trees. So for a regular binary search tree, the average time complexity of insertion, deletion, and searching are all log n, which is great, right? Like that means that, yeah, we can do all those operations and all of them are done in log n time. However, the worst case for all of these is O of n time, because these trees may not be balanced. So for example, we can have a tree, a valid binary search tree even, like let's give it numbers. So maybe we have 5, 6, 7, and so on, right? And it's just, let's say 8, 9, and so on, right? Notice this is a valid binary search tree. The problem is it's unbalanced. And what we mean by not balanced is with a balanced binary search tree, we're expecting like every subtree to have about the same height. And like, this is just basically a linked list, right? And so for insertion, deletion, and searching, it's going to take O n time because you have to go through the whole list potentially to even find what you're looking for. So the worst case time complexity for an unbalanced tree is O of n. And I mean, that's not very good because we want to have this average time complexity be a guarantee. That would be great. So how do we do that? Well, that's why balanced trees are useful. So what's balance? So balance is when, okay. So the balance of the tree is, it refers to the height of the left subtree minus the height of the right subtree. And this is true for every node, right? So we calculate the balance value, and that's the balance factor. So balance factor is just height of left minus height of right. So you take any node, get the height of its left, get the height of its right, left minus right, that's your balance factor. I mean, you could do height of left minus height of right, could do height of right minus height of left. The only thing that really matters is the magnitude of that number. So yeah, like as long as you're consistent with it, in these slides, we're going to do height of left minus height of right. But to find whether a tree is balanced, it's also perfectly fine to height of right minus height of left, as long as you're consistent with it. But in these slides, we're going to do left minus right. And yeah, we'll do left minus right here. Okay, and let's just look at how we calculate it. So down here, in this example, we're doing, if we look at node 1, right, this node, the balance factor is -6 because you do height of left minus height of right. The height of the left subtree is how many nodes, the height of the left side, right? So how many levels are there on the left? 0. How many levels are there on its right? 1, 2, 3, 4, 5, 6, right? So we do height of left minus height of right is -6, right? So our balance factor is -6. And of course, like we would, for knowing whether it's balanced or not, like it doesn't really matter whether this number is like -6 or +6. In both cases, we know it's not balanced. And that's why this order of which one you subtract from the other, it doesn't matter. We're really only concerned with the fact that even though it's -6, we're really concerned with the fact that like it's 6, which is not what we want. Meanwhile, if we look at this one over here on the right, node 4 has a balance factor of 2 minus 2, which is 0, because the height of its left is 2, right? And the height of its right is also 2. So 2 minus 2 is 0. But maybe just for practice, you can maybe ask yourself, okay, what's the height of, or not what's the height of, what's the balance factor of this node here? Node 5. And if you're here, you can also try and answer the question, so yeah, what's the balance factor of 5 here?
-2.
Yep, exactly right. Yeah, awesome. So yeah, because subtrees can also have balance factors, it's not just the root we care about. And here it is -2 because the height of left is 0 and the height of right is 2. Okay, so now we have that out of the way. Now we can kind of understand why balance is important for balanced tree. And maybe you can kind of already get an idea, maybe you kind of are thinking, okay, well, clearly the one on the left here is not balanced. The one on the right kind of looks like it's balanced, right? It looks like, okay, kind of like a perfect tree, right? Well, it is a perfect tree. But maybe you're kind of thinking that to yourself. So, and if you're thinking that to yourself, awesome, that's great. Because that's exactly what we care about, right? If this number is too large, like -6, the magnitude of it is 6, right? That's really large, then it probably isn't so balanced. But if the magnitude of all of them is kind of small, it probably is balanced. So that's how we're going to worry about balance. Okay. So what about balanced binary search trees? Well, we can see already that they're better because every node in a balanced binary search tree has a balance factor that's -1, 0, or 1. And that's a really useful property, right? Because if we just look back, right, like that means this one on the left, right, is not a balanced binary search tree, but the one on the right is. And that's going to guarantee us, ensuring this is going to guarantee us that the height of the tree is only log n. And if the height of the tree is log n, then finding a node is only going to be log n, because you only have to go through the height of the tree number of nodes to find what you're looking for as a maximum, right? To go all the way to a leaf is only going to take log n time. And insertion, right, into a binary search tree or deletion from binary search tree, I mean, only takes the amount of time that insertion would, right? Or not insertion, insertion and deletion only take as much time as like finding them would. So it's going to be log n, right, for all three, which is really nice if we can guarantee that it's balanced. So balance factor again is height of left minus height of right. And if that's -1, 0, or 1 for every node in the tree, it's balanced, and we can guarantee that not only is the average time complexity for all three of these operations log n, but the worst case is also log n. Yeah. Okay. So we look at the left here, right? And we see an unbalanced tree. In the worst case, you have to iterate through 7 nodes. Well, that's pretty bad, right? Because we can just as well, we have the same 7 nodes here on the right, and it is balanced. And notice you only have to go through 3 nodes. So that looks a lot better, right, on the right than it does on the left in terms of how many operations your code is going to have to do. And if you think about really, really, really large trees, right, this is only, the one on the left is only going to get worse. But the one on the right, it only scales with respect to like log n, and the one on the left scales with respect to n. So the one on the right, you're not going to add that many levels, but the one on the left, you absolutely are. And so having a balanced tree does make a big difference. Okay, so we're talking about rotations. And the reason why we're talking about rotations is because you may think, okay, so this is great, right? Like balanced trees sound like awesome, and they are, right? But how do we ensure that when we insert something, the tree stays balanced? Like you can't just insert something and hope it's balanced. That's not good enough. So we can ensure that it's balanced by using rotations. So rotations move nodes around in a binary search tree without violating its properties. So this allows us to make sure that it remains a binary search tree and that it remains balanced on insertion and deletion. And yeah, this makes it balanced, so future operations will be more efficient. So there are 4 types of rotations. First kind of rotation is a left rotation. We have a right rotation. We have a left-right rotation. We have a right-left rotation. Those are 4 types of rotations. Okay. And yeah, the nice thing is all of these rotations have O1 time complexity. So what that means for us right, is like, even though we have to do these rotations to keep the tree balanced, it's not going to change the time complexity. Like on an insertion or a deletion, or yeah, on insertion and deletion, we might have to run these right, left, right, left. We might have to do a rotation, but the rotation itself doesn't add a lot of extra time to the program. And so as a result, it doesn't affect the time complexity. So the worst case time complexity remains log n because these operations only take one. So that's kind of nice to have. Okay, I don't know why that didn't move. Okay, but now let's talk about the first type of rotation. First type of rotation is a left rotation. And so a left rotation occurs when you have your binary search tree, right? And at some node, you have an imbalance, in which like you have the balance factor of this one is like -2, and its child's balance factor is -1. And in that case, it'll always be a left rotation that you need because it's a right case. And so that might sound confusing. So I think visually it helps a lot more. So let's look visually. Like these are the way we'd write it into a program. We can check if the parent is -2 and the child is -1. So that's the kind of thing you would do like on a project, right? But I think like if you're just looking at it, this is an easier way of understanding it. So if you look and there's some node which has this right imbalance in which you have a node, right? And they have another node to its right, another node to its right, but you don't have anything on the left of this guy. Like you have some subtree rooted here. There's something to its right, which has something to its right. But the original one has nothing on its left, right? That's a right. And that's all. That's how we know it's right. So like even just looking at it, right. That's it, yeah. And when you have a right case, you need to do a left rotation. So I like to think of this is kind of like visually. So imagine these are like, I don't know, like this 1, this 2, and this 3 are like balls on a string. So if you have like a string and you pick up the 2, then like the 1 is going to go to the left and like the 3 is going to go to the right. So you like pick it up and then you have the 2 here and like 3 here. And that's exactly what we get. And notice that this gives us a valid binary search tree. 2, 1, 3, it's valid. So that's how we do a left rotation. And now we're going to talk about a right rotation. So a right rotation is just the inverse of a left rotation, in which you have a left case. So left case, you have your subtree rooted at 3, and you go left and left, right? And the way we program that into a computer, right, if we want to check if it's left for a certain node, is when the parent's balance factor is 2 and the child's balance factor is 1. And in that case, what you need to do is just the opposite. Like you pick up the middle one, move it to the top. The one at the top goes to the right, and one on the left goes to the left. So yeah, that's about it. It's just like that. And notice this is a valid binary search tree. Okay. The next two are a little more complicated, but they use the exact same ideas. They're just building off of what we already saw. A left-right rotation is what we use for a left-right case. If you remember, left case, right rotation. Right case, left rotation. But left-right case, left-right rotation. So for left, and right, we flip, so it becomes left, you do a right rotation, right, you do a left rotation, but left, you do a left-right rotation, and right, you do a right-left rotation. Okay, so that was a lot of words, but hopefully that made sense. With the left-right case, you have something goes left, and you have something goes right. And again, in your computer, right, we program that it's like parent, when parent has balance factor 2, child has balance factor of -1. And this requires us to do 2 rotations, right? And one is a left rotation, about 1. And the second one is going to be a right rotation, about 3. So yeah, it's just a left-right rotation. It's called that because you do a left rotation followed by a right rotation. We think of it as just one operation because it's a certain case. So, okay. But we have 3, 1, 2. So the way we're going to do this is first we're going to move. This one is a little harder to see visually. Like I can't really see it visually. So what we can do instead is we can kind of just look at it and try and get understanding. So what we want to do is we want to get it into this position. We want to get it into a position in which all we need is one right rotation. So the way we do that is we kind of move the 2 up to where the 1 is, and the 1 goes down. And so we have 3, 2, 1. So we do a right rotation about 1, and then a left rotation about 3. And then we have our left case, and from there it's just a right rotation, which we already saw. I will point out, for me at least, like sometimes when you have smaller problems, the easiest way to do it is kind of in your head. If you're given like a tree and you need to kind of figure, okay, what kind of rotation, or what is the rotation going to look like? I think sometimes for me, it's just easier to look at it in my head. So if I'm given this, right, I notice first of all, it's not balanced, right? So what kind of configuration of these 3 nodes could I make to make it balanced? Well, I put the middle, like if I put them in a list, right, in ascending order, I would have 1, 2, 3, right? Okay, so I take the middle element, which is just 2. I put the smallest one on its left and the larger one on its right. And visually, I think that kind of helps me. That's not really what's going on. Like you have to do these rotations, but if you have to like figure out, okay, what's the rotation going to look like afterwards? I think this helps kind of see, okay, this is what the rotation is going to look like afterwards. But now the right-left rotation is in the right-left case. And it's the same thing, it's just, again, the inverse of the left-right rotation. So we have right-left, the 2 moves up to where the 3 is, the 3 moves down, and we do a left rotation about 1. So we have a right rotation about 3, and then a left rotation about 1. And then that's it. Okay. So when do we use each rotation? Well, we use a left-left if these, like, you can use this table for like to figure out what the balance factors are, like left-left, parent plus 2, child plus 1. And those are definitely good to know, especially if it's a good like cheat sheet if you're like writing code, right? But also, it's also good to see, okay, the case is left-left, I do a right rotation, right-right, left rotation. And then for left-right and right-left is the same as the case. And for all of these, we're doing balance factor is height of left. Okay, so that's how we do rotations. How do they like do us any good? Well, okay, well, oh, oops, didn't mean to go forward. Well, how do they do us any good? Well, you can kind of see, right? This balances the tree, right? Like I have a subtree, which originally was height of 3. This changes to height of 2, which is awesome. So maybe you saw this answer, but for this, notice there's an imbalance in the left subtree, 4, 6, and 8. So you can go ahead and pause and try and figure it out if you're here to try and answer. What kind of imbalance is it? What rotation fixes it?
C.
See, yeah, absolutely. That's right. And as Rachel noted, it's a left-left case because at 4, 6, and 8, we have 8, and left of that is 6, left of that is 4. So it's a left-left case. And the way we fix left-left is right rotation. So at the end, it should look like 6, 8, 4. So C. And we can also figure out by looking at balance factors and look at our table, right? 2, 1, 2, and then child being 1. That gives us left. Okay. This one's very similar kind of question. For the subtree, yeah, so notice we fixed the left one, but now on the right subtree, 14, 11, and 12. What imbalances it? What rotation fixes it?
Left, right, and left, right.
Yeah, absolutely. Yeah, that's exactly it. So at 14, right, go left and go right. And the way we fix left, right rotation, left, right. Awesome. And again, if you know this based on balance factors, that's also okay. 2, negative 1, 0. Tell this left, right case. And we perform the rotation. So the first part of the rotation is like moving the 12 up and the 11 down. So we do like a left rotation about 11. And then we do a right rotation about 14. And then we have a balanced tree. Okay, so question 3. What rotations does this tree need? This one's definitely a little bit trickier. All right, I can try the third if you're.
Hold on just a second.
Okay, yeah, sure.
Right, or like you do a right and a left. I don't think it matters which order you do them in. So
Okay.
D.
Okay. So let's actually go through this. So this one is actually really tricky for sure. Like I know when I first saw something, so but yeah, like the rotations that it needs. Well, in order to know if it needs a rotation, we have to have a balance factor that has magnitude at least 2. If there's a balance factor is only 0, -1, 1, it's balanced. So what we notice is the balance factor of the root is 0. And it's 0 because the height of left is 2, height of right is 0. It's 2, so 2 minus 2 is 0. And then 5, height of left is 1, height of right is 0, so 1. -1's for 17 and 0 and 0. So even though like it looks like we might need both right and left, like to fix both of the sides, this is actually okay. This is perfectly fine. This is balanced. So the answer would be none. So let's go on to the next question. Yeah, none. Try to balance. Okay, so for this one, what rotations are needed at A and B?
At A, we need a right left. And at B, we need a left.
Yep, absolutely. That's exactly right. So right, left at A, and then a left at B. And it's gonna, well, I guess we don't see what it looks like. That's okay. So we can go and move on to question 5. So what's the worst case time complexity for inserting into this tree? And to make it more clear, right, assume this tree like just keeps going, like it doesn't stop at 5.
Oh, then.
Nope, exactly right. So this is an unbalanced tree, right? And so it's basically just a linked list, right, of nodes, and the time for finding or inserting or whatever into a linked list is worst case event. So D. You can kind of see that here. Tree is unbalanced. Worst case, have to go through all n elements. So worst case simplicity is D of n. And searching and deletion in an unbalanced tree also O n. Okay, another question. So worst case complexity of searching in this binary tree.
Log n.
Yeah, that's exactly right. It is log n. And we can kind of see why, right? Because this is before you're dealing with an unbalanced tree. We can kind of see this one is balanced because the balance factor of this one, right, is -1 for this node 2. And balance factor here is 0. Balance factor here is 0, 0, 0. So this is a balanced tree. And since it's a balanced tree, well, if we have a balanced tree, inserting into it just takes log n 10. Or I guess it's a searching. Well, searching and searching and deletion are all at the same time. Let's see for balanced trees and unbalanced trees. Yeah, so the worst we have to do is go through log n elements. So the worst is C. Okay. Now we're into my AVL tree. So AVL trees are a type of balanced binary search tree. And really the rotations we've been talking about today are most relevant for AVL trees. Like that's what AVL trees really are. Like they use these rotations. Like other balanced binary trees, like kind of do their own thing, which we'll talk about more examples later. But like primarily what we've been talking about today is relevant, especially for AVL trees. So as an AVL tree, so first of all, it's a self-balancing binary search tree. So it's a binary tree, but it's also a binary search tree. So if I gave you a balanced tree, right, and it's balanced, but it's not a binary search tree. So if I give you something like this, let's say 4, 1, 5. Like this is a balanced tree, but this is not an AVL tree because it's not a binary search tree. Okay. And it's not a binary search tree because, well, the 5 is on the left of 4 and it's greater, and 1 is less than 4, but it's on the right. So yeah, but AVL trees are a self-balancing binary search tree. And every node has a height or balance attribute, which can be updated in an insertion or deletion based on the placement of the new node. So just like we saw before, where we had to do rotations, those rotations occur in an AVL tree after you insert or delete. And after each insertion, you have to only do at most O of 1 rotations. And really, you only have to do 1 rotation. If you count like left, right, and right, left is just 1, then you'll have to do 1 rotation. Otherwise, you might have to do 2, which is right and left. If you consider like right, left to be 2 separate rotations, then you have to do 2. But if you consider only to do 1, then it's really just 1 rotation you have to do. That's it. If you insert. For deletion, if you want to keep it balanced, you have to do log n rotations. That's because like if it's removed from, like if you have a tree in which it's perfect, but you add an extra node on the end, and then you delete one all the way on the other side, then you're gonna have to balance all the way up to fix it. I mean, that's not really too important. Don't worry about why, but yeah, for insertion, it's at most O1 operations, rotation, or at most O1 rotations. And deletion, don't worry about too much, because I think on your project, you don't have to worry about balancing after deletion, because that becomes more complicated. But the same idea still applies. Like it's still the same idea. So yeah. Anyway, so since an AVL tree stays balanced, its insertion, deletion, and searching are all log n, which is kind of nice. Okay. That's a balanced binary search tree. And all elements have to have balance factors of -1, 0, 1. And that's a key thing for AVL trees. Yeah. So let's talk about another kind of balanced binary tree. Okay, next, first we're going to do this. We're going to look at insertion and adjustment example. So if I have this tree originally, it's 2, 3, 1, and 4, and I insert a 5 into it. Well, this 5 is going to go, well, it's larger than 2, right? So it goes on the right of 2. Well, it's larger than 3, so it goes on the right of 3. And it's larger than 4, so it goes on the right of 4. So we have this, right? 2, 3, 4, 5. And notice there's an imbalance. The imbalance doesn't have to be at the root. Like here, we notice the imbalance is actually at 3, right? And there's an imbalance at 3 because we have a right-right rotation, or not right, sorry, right-right case. So we need to perform rotation. That's, as I mentioned before, right-right case, left rotation. So we inserted 5, it's no longer balanced. So we iterate all the way. The way this works, the way an AVL tree rebalances is it starts where you inserted, and it's going to work its way back up and find the imbalance if one exists. And it finds this imbalance at 3. And when it does that, it's going to have to rebalance, or have to do a rotation to fix the balances, right? And the way it's going to do that is it's going to do a left rotation. So the 4 is going to move up, 3 is going to move to the left, and 5 is going to move to the right. We wind up with this as our subtree. So it fixed itself and it's balanced again. Yay. Okay. Now we're talking about another kind of balanced binary tree. So the main one that I think is the most important for us to know in this course is AVL trees. There's another tree that like you might have to know a little bit. We'll talk about in a second. Red-black trees. You don't have to write code for red-black trees because red-black trees, let me tell you, they are difficult to write code for. Yeah, I had to do it for one class. It took me a long time to do. It's just difficult, but they're very similar to AVL trees. They just have 4 rules that you need to follow. And this is the main thing you need to know about red-black trees, are really like the only thing that I think is really important that you guys know for this class from red-black trees. The only kind of thing we'll ask about are these 4 rules. So as long as you know these 4 rules, you should be fine. So for red-black trees, a node is always red or black. We just color them. So the colors we assign them are going to be red or black. The root is always black. A red node has black children. So all that means, and this whole null reference considered a black node, all that means, all this whole bullet point means is that you don't have 2 red nodes in a row. So anytime you have like a path from root to leaf, you can't have 2 consecutive red nodes. Like a red node can't have a red child. But it's like, and this other part is saying that it's okay for a leaf to be red. That's what this in parentheses is saying. I don't know why it sounds so complicated, but it's just trying to say a leaf can be red. And the number of black nodes in any path from root to leaf is the same. And so that's actually pretty interesting, because what this is trying to say is that for any path you take, so any sequence of nodes that you start at the root and wind up at some leaf, the number of black nodes along any of those paths is going to be the same. So whether I go like I start at the root and I go left and then I go right or whatever until I reach a leaf, or whether I go like right and left and left, it doesn't matter. Whatever order you take to get from root to leaf, we're always going to go see the exact same number of black nodes. And red-black trees like have some distinctions from AVL trees. So for one thing, the nice thing is that you don't have to, like on deletions, you don't have to do as much balancing or as many rotations to balance, which is nice. But it may, like the balance factors may not always be -1, 0, 1. It does guarantee balance, but it may not have only those numbers. But that's red-black trees. You don't need to know what I just said. It's just these 4 bullet points that I think are most important. But some applications are scheduling algorithms, but also backend C++ maps. So ordered maps in C++ are just, well, I guess they're just maps, right? So the ordered maps are just red-black trees. That's what they are. That's pretty cool. Okay, so question 7, which of the following are true about a red-black tree?
A and C.
Yep, that's exactly right. So A and C are correct because a node is always red or black, and the number of black nodes in any path in which it's the same. The red is always red is not true. The red is always black, and red and black trees are. I mean that's yeah, true. And the last one, if a node is black, its children must be black. That's not true because it's if a node is red, its children must be black. I mean, if this one were true, then that would mean that every node is black because we already know the root is black. But anyway, yeah, it's just ants. Okay. Those are the answers. All right. The next thing we're talking about is splay trees. So what are splay trees? So splay trees are another kind of balanced binary search tree. And the interesting thing about splay trees is that splay trees rebalance after every time you access something. So the real use for splay trees is like for caching and things. It's like if you want to get the most recently accessed node, right? It's going to be the one at the root, which means if you're accessing the same kind of data a lot, it's going to all be near the top, which is good because you're going to want to, like, if you're accessing something a lot, you want it closer to the root because then you don't have to go as far through the tree. So it's like, if it's the root, right, you only have to check one thing. It's at the root. You don't have to go through login things, just the first thing. So that's kind of useful in some cases. So this, you don't have to know too much about splay trees. It's really just the fact that they do zigzag rotation. So after you access a node, you do zigzag rotations to make the most recently accessed thing the root. That's really all you need to know about splay trees. And yeah, it's for ensuring that most commonly accessed nodes have least access time because they're closer to the top of the tree. Okay, so what about B trees? So B trees, so this is the other kind of tree that I think you guys need to know a little bit about. Because yeah, there's like the other ones are good to know too. I think like B trees, it's kind of good to know how they work a little bit. So, or what they are. So I'll get into what you need, but so B trees are a self-balancing tree, but they store key values. So they store huge amounts of data for fast query and retrieval, and it's an n-ary tree. So rather than like being a binary tree, it's an n-ary tree. So it's just every node can have more than 2 children. You can have multiple key value pairs in a node, and it's sorted descending. So, okay. So what does all this mean? So, okay, actually, interestingly, each node in a B tree, right, can have multiple, or will have multiple values in it in many cases, right? It's going to have multiple values, like we have 15 and 20 here. And the interesting thing is that the way that you store nodes in a B tree is with a balanced tree itself. So usually, like within a B tree, each node is usually done like with a red-black tree. That's just an interesting side. That's something you need to know. But yeah, B trees are an n-ary tree. Each node has multiple values, but also keys. And really, key value pairs in B trees just means that these are values. Like, just assume these are all values. Each of these is a value. We'll see what the difference is and why we specify that a couple slides from now. But don't worry too much for the moment. They're self-balancing, and they store key value pairs. Okay, and notice also internal nodes are nodes which are not leaves. You have your root here, you have internal nodes, and you have leaves. And leaves are the thing at the last level. Or like they don't have children. Nodes that don't have children. Okay. So what are some properties of B trees? So these are properties of B trees. You can memorize if you want, but I think it's easier if we kind of go into an example next. So first, let's just look at this. So, I mean, we can look at them first and we're gonna do that, but don't worry too much about the specifics. We're gonna kind of get a better understanding in a minute. So important properties of B trees. All nodes have at most n children. So we're given some variable n, right? All nodes have at most n children. It's an n-ary tree, right? So yeah. The root node is either a leaf, right? So it means it has no children, or it has somewhere between 2 and n children. Internal nodes have somewhere between n over 2, scaling of that to n children, and non-leaf nodes have a maximum of n-1 keys. And L is the number of keys a node. Okay. So yeah. So let's just draw this out. Let me go over kind of an example really quickly. So yeah, as an example, we can look at, let's say that I have L equals 2, or let's say the height of it is 3, right? Or so the height is, I guess, 2, so it has like 0, 1, and 2 or something. Let's say L is 2, right? Maybe we have a tree like this, 5 and 10. And the way this works, and maybe n is 3. Yeah. So the way this works is that you have each of them, this can have at most 3 children, right? Now each of the children will have 2 values, right? L equals 2. And let's say I have like, I don't know, 4 here, or no, let's say like 2 here and 4 here. So this is going to have 3 children, right? This 5, 10 thing. Say it's like 6, 7, and 11, 12. But what's going on is that of the 3 children, this has 2 values, right? So the value to the left of, like the thing to the left, the node to the left of the 5, everything is smaller than 5. The one in between 5 and 10, everything is in between 5 and 10. So as we see here, 6 and 7 are between 5 and 10. And the one to the right, everything is larger than both 5 and 10. Okay, but now let's suppose that I ask you to insert a 13. So if we insert a 13, let me explain how this works. So when we insert a 13, what's going to happen is we're going to say, okay, is 13 larger than, well, we can do binary search on it, but let's just say we're doing a linear search. We're going to say, is 13 larger than 5? It is. Is 13 larger than 10? It is. So 13 is going to go ahead and go into the right child of this node 510. Okay. So this node 510, 13 goes into the right child. But notice this right child is already full because it already has 2 things, and 2 is the maximum number of things that we can have, number of values. So what it's going to do is first we're just going to put it in there as if there was no problem. So we're going to put 13 there. We notice now there is a problem because this thing is overfull. And because it's overfull, you can't do that, right? You can't have more than 2. So the solution is it's going to take the middle value and it's going to move it up. And so what this is going to look like is this. So after it adds a 13, it removes the 12, right, and moves it up the tree. So this 13 remains here. But this 12 is going to be added, and we're going to add it into whatever place it fits in. Here, it's going to go here. So far, we're like, okay, we're good, but we're not, because this top level has 3 values. But we said that the maximum number it could have was 2. It's n minus 3. Okay. Because have a maximum of n minus 1 keys. Well, n minus 1 is 2, so this is no good. So what we need to do is, again, take the middle value. If the node is overfull, and this node is overfull, we take the middle value and move it up the tree. So let's do that. So again, we take the middle value, move it up, and now we have this as our tree. Okay, and so maybe that was a little bit confusing, but hopefully you kind of saw how that worked, where when we inserted something into the tree that made a node overflow or like too big or overfilled, right? What you do is you take the middle element from that node. If the node is too full, you take the middle one, you move it up to the parent, and then you put it in the parent. And then if the parent becomes overfull, you take the middle one, move it up to its parent. And then if that node is overfull, you move it up to its parent and so on. And eventually the root is overfull. So you take the middle one and it's your new root, and that's it. Okay. So
in this
yeah,
like example that you just made,
Mhm.
like didn't you say that like the arrow, like if since that arrow is after the 12, the numbers are going to be greater than 12, but then it's 11 and 13?
Oh yeah, that's a good point actually. So yeah, so I guess my statement wasn't completely right. It has to be, so 11, okay. So it's possible that some of the values could be smaller after an insertion. You're right, actually. That's a really good point, because that does
Wait,
contradict what I think.
did you say to move up the middle node or the leftmost? The leftmost.
You move up the middle one. Yeah.
Okay.
Yeah. But yeah, that's a good point, actually. I think moving up the smallest one would work also, so that would be a solution. But I think, yeah, for the purpose of this, I think actually that might work better. But yeah, like for the purpose of this, we do move up the middle one. That's another approach to take. And yeah, so you move the middle one, but good point. Cool. So, right. So that's how B trees work. And moving on, we look at B plus trees. So that was how B trees work, and B plus trees are very, very similar to B plus trees, or B plus trees are very similar to B trees. We'll see why. Because a B plus tree is just a B tree, but with the following rules. Each node contains only keys and not pairs of key values. And all data is stored in the leaves. So remember how I said there's a slight distinction between key value and key? Yeah, so, okay. So bear with me for a second. So in a B tree, right, if this were a B tree and not a B plus tree, then what this would be is that these values here would have some meaning, right? And they would have, like if I'm looking for data, data might be stored in one of the internal nodes, right? This 18 might be the data 18. But in a B plus tree, this 18 is not actual data. It's just a way, it's just there to tell you whether to go left or right if you're trying to find something, right? Like this 18 is just there to tell you, okay, like it's just there to help you. Like with a 6, for example, right? This 6 just helps you find out, okay, do I go left or right? But this 6 here is not an actual data point, but this 6 is. Okay, so that's the thing with B plus tree. So in a B plus tree, you might have, even if you only insert every element one time, you might have an internal node that like is a 5, but then the actual value 5 might be in a leaf. So internal nodes in B plus trees don't have like the meaning that they do in B trees. Like in B trees, data can be stored in internal nodes, but in B plus trees, that's not the case. Okay, and all data is stored in leaves in B plus trees. And what that means is like, yeah, all of the data, so all the data we actually care about is only in leaves. And we link together all of the leaf nodes as a linked list. So 1 through 4 links to 5, links to 6, 10, 12, links to 15, 16, links to 18, 20, 25. Okay. And yeah, and then at the end it links to null. So that's how B plus trees are. And also additional level is added at the bottom, and that's where you have your linked leaves. So that's the difference, is that B trees, every single like key or data point, like every single key also has some meaning, like some data. But in B plus trees, Only the leaves have data. Okay. So, okay, we can kind of look at that and be like, okay, so why would we use B and B plus trees? Well, data is pulled from external blocks, so it allows us to have like really large groups of data. So maybe you have external cache blocks, and the applications of them are indexing file systems or databases. So a question is, you can pause and answer if you're at home, or if you're here, you can try and answer. Which of these is a B tree and which is a B plus tree?
The first one is the B tree and the second one is B plus.
Yeah, that's exactly right. And even there, what we might notice is that this like 3, right? This 3 is not the data 3. This 3 just like helps us know, okay, the 3 is somewhere below me. And like that's where the 3 is. Whereas this 3 is the actual value. Like both of these have only, like both of these trees have only 0, 1, 2, 3, 4, 5. Okay, this one also has a 6. Fine, as their data. But this one has a data at leaves. Okay. But yeah, tree 1, B tree 2, B plus tree. Okay. So these, okay, yeah. B plus trees, damn it. And a B tree doesn't have duplicates. Okay, so these we're going to go over together. It's just a question, but we're going to go over these together because I think this is kind of the main thing that I think is most important for everyone to know how to do with B and B plus trees. And we haven't really gone over this specifically, so we're going to go over this together. So you're given a perfect B plus tree. So perfect, it's a perfect tree, right? With n equals 3 and l equals 3 and a height of 2. How many unique keys are there? So we calculate this for a B plus tree. It's like this. So first of all, notice l equals 3. So L is the maximum number of keys in a leaf. And n equals 3. So it's a perfect tree. So n is the number of children every node has. And n minus 1 is the number of n minus 1 is the number of keys that each internal node has. That makes sense. So let's try and figure this out. So we have the root. Well, the root is not a leaf. So say internal node, right? And how many keys is it going to have? Well, if it's a perfect tree, we're going to take the maximum. And the maximum is n minus 1 keys. So let's do that. So let's say we have the maximum number. So non-leaf nodes have up to n minus 1 keys. Well, n minus 1 is 2, right? Because 3 is minus 1, 2. The height, remember, is 2, so it has levels 0, 1, and 2. So really, like I guess height is kind of 3, but we say 2, it's fine. We'll always specify what we need for that. And now n equals 3. So this root node can have 3 children. So we're going to draw 3 children. Oh, this one was bad. Okay. But these children themselves, excuse me, are not leaves, right? Because the height, like this is level 0, there's level 1, so we need another level. So these aren't leaves, these are internal nodes. And remember, internal nodes can have only n minus 1 keys. So 3 minus 1 is 2. 3 minus 1 is 2. Minus 1 is 2. And now each of these also has 3 children because it's a perfect tree, and n equals 3. But remember, leaf nodes can have maximum L keys. L is 3. So these have 3 each instead of 2. And what we notice is that from the previous level, on the previous level, each of them have, there are 3 things on the previous level, and each of them have 3 kids. So 3 kids, 3 each, that's 9, right? We're gonna have 9 nodes. But how many keys are there in each node? 3, right? We notice in the at the leaves, because L equals 3, each of the nodes has 3 keys. So there are 9 nodes to leaf, each with 3 keys. 9 times 3, 27 unique values. And 27 unique values because it's a B plus tree. And B plus trees, if you remember, only have unique values in the leaves, not anywhere else in the tree. So we don't actually worry about the rest of the tree. So we wind up with 27 as our answer. Okay. Does that make sense?
Yes.
Awesome. Glad to. So now, okay, maybe we can kind of say, okay, that makes sense. But what about All right, so we have 27, right? And we're going to see visual representation. 2 keys, 2 keys, 2 keys, and then each of those has 3, each with 3 keys. But what about now? Let's change the problem. It's exactly the same, but instead of it being a B plus tree, it's a B tree. So now the problem changes a little bit. So we're still asked about the unique keys in the tree. But what do we know about unique keys in B trees versus B plus trees?
We also count the keys in the internal nodes.
That's exactly right. Yeah, perfect. And so if we count the ones in the internal nodes, how many are we going to get?
8.
That's right. Yep. 8.
We add that to our 27, and we'll get 35D.
That's exactly right. Yep. 35. Okay, so we have 2, 2, 2, 2, 2. 4 of those. That's 8. Plus the 27 we already had. So 35. Perfect. So we end up with 35. Okay. And seeing the visual representation. It's like this. They're kind of confusing. How do we get used to them? You can absolutely use these visualizations. They can help. And you can try and like put things in and see how it works. Okay. So now let's look at a coding question. So for a coding question, you're presented with, let's just do this coding question, right? It's like, we're presented with a perfect binary tree whose node pointer looks like this. You have a node, has a value, has left and right. So far, up until line 5, just a normal node class. But then there's a next pointer, line 5. So what does that mean? Well, we want to connect together each pointer's next value to the node to its right. So like as an example, let's look at this below. Like 1's next is null, has nothing after it. 2's next is 3. 4's next is 5, which is next 6, next 7, next null. So based on like this picture and the problem, maybe you can, if you're online later and watching asynchronously, you can kind of think, okay, what exactly would I use to solve this? And if you're here now, maybe there's something like something we talked about in the previous week that like maybe you'd use to solve this problem. If you have any ideas. Well, we can kind of think to ourselves, right? Well, if you want to say something, you can.
Like level order traversal.
That's exactly right. Yeah, perfect.
Yeah.
So yeah, absolutely. The way we would solve this is with a level order traversal because, well, if we go through the level, right? 1's next in the level is null. 2's next in the level is 3. 3's next is null. Then 4 next, 5, 6. And we're just going level by level, and that's it. So we can just code this up, and we'll look at the code here since we're a little bit short on time. So we're going to look at the solution, and notice this is still just a level order traversal. You have your queue. If the root is not null, right, then you're going to push the root onto your queue. And then while your queue isn't empty, you're going to have queue.size as the number of elements in that level, right? So count represents the number of elements at the level you're currently at. And then you take the node from the top of the queue and from the front of the queue. You pop the top of the, or you pop from the front of the queue, and you're doing the same thing as you usually would with the level order traversal because you're going to add its children to the queue. But first, you also check if it's the last thing in the level. So if count I equals count minus 1. So if you just remove the last thing from the whole level, then you say it's next to null pointer, right? Because this next pointer should be null if it's the last thing. However, if it's not the last thing, then we can just take the next thing from the queue and make that our next. So going back here, right? If we have 5, for example, if we're at 5, we can just take the next thing from our queue. Well, 6 is the next thing in the queue. So 5's next, we're going to point to 6, right? 5 to 6. And that's it. But for 7, for example, right? There's nothing after it in the queue because it's the last thing at the level. So we're going to point 7 to the next thing in the queue. There's nothing next in the queue. So we can't, right? I is equal to count minus 1 in that case. So rather than adding it to or pointing the next thing in the queue, we're just going to point the next thing to null pointer, which is exactly what we want, right? 7 goes to null. Other than that, though, it's just a regular level or traversal. So any questions about that? If not, then I think that's everything I have for today. I guess I'll stop the break.